So it is a great pleasure for me to introduce this year's Flajolet lecturer, Mikhail Drmota. I hope that Flajolet doesn't need any presentation here. We all know his important work in both creating much of analytic combinatorics and also having a large part in creating this community here. But we could say the same with Michael here. He has also done a lot of work in analytic combinatorics, and I would say it is my perspective, he's really followed in the steps of Flajolet, so it's very natural Flajolet lecture from that perspective, unlike, for example, last time Flajolet lecture doing something else. But he has, Michel has also been important in doing much work here with the analysis of algorithm community in various ways. So I think I'll stop there and let Michel go on with his lecture and let his mathematics research talk for itself. So please, Michel, my congratulations.
Thank you very much. Thank you for this kind words, Svante, and thanks for the whole committee that I was awarded this Flajolet Lecture Prize. It's a big honor for me to speak here in this occasion, also because of this prize, and it's a big pleasure being here. And I was already in the first meeting in '93 in Dagstol, and I attended all of these 35 meetings, I think. So this community was very important for me, always a spring of inspiration, and many thanks to all of you. And there are so many co-authors and friends here. So let me get started with the talk. And maybe I should have changed the title of the talk, The Method of Moments. Revisit, I'm sorry if my English, I'm not a native speaker, so I will call it the moment method. Sorry for that. So this is just it is cumulative in some sense. So, well, and the idea behind the problems that I want to consider have been already mentioned today in two talks, the first one by Gabriel and the second by Wenchi. You have a big structure, discrete structure, and you look for some specific situation that appears in this big structure, and you count how often it appears. So this is the idea behind what I want to talk about, and you will see it from the examples and also from the main result that I want to present. That is a joint work with Eva Maria Heinzel and Nick Wormold. So let me start very classically. So what is the average case analysis in analytic combinatorics? So of course I start with generating functions. So this is just the counting generating functions. But usually you're interested in the distribution, or at least the average behavior of some parameter. So you have to split. So you have C and K, the number of objects where some parameter has value K. And then you usually introduce some randomness to say every object is equally likely of given size. And then you have the random variable that describes this parameter. So you just define the probability of this random variable in this way by this fraction C and K over Cn. And of course, you can also write down the bivariate generating function that captures all the information. And this can be written also in the form that you put here the probability generating function of this random variable xn times Cn as a coefficient. And then, for example, by computing the first moment or the expected value, so the average case of this random variable xn, you just have to take the derivative with respect to u of this second variable, evaluate it at 1, take the coefficient in respect to c, the nth coefficient divided by the nth coefficient of c of c1, so which is just Cn, and that's the first moment, say. And this is the starting point. Of course, the first moment is not the most important parameter, but gives you a hint how a first hint how a random variable or some parameter behaves. So what you're interested usually is then the behavior of this parameter, the distribution, and you, for example, you want to prove some weak limit of this random variable. So there are various ways of defining weak limits. So by functionals or by the characteristic function or just by the distribution function. So this is just basic probability theory. And of course, this characteristic function here is related to the probability generating function just by setting u to e to it. And the method of moments, or moment method, is just the following theorem that if you want to prove the distribution as a weak convergence in distribution, then it's sufficient to prove convergence of all moments, provided that the moments of this limit define uniquely the distribution. So, for example, the central limit theorem can be proved in that way and many others. So let me state just one example here. There are many others going back to Flajolet and Rudlitsky from 1982, where they characterized the distribution of the height in binary trees, and they did it with the method of moments. So they computed all moments of this random variable. So the height divided by 2 times square root n, and this has the moments have some limits, and these limits are moments of a so-called theta distribution, and this can be given in various ways. There are various ways of expressing the distribution function or the density of this distribution. Of course, later it was clear that it has to be of that kind. So after all those, we know that there is a continuum random tree, that the height is related to the maximum of the Brown excursion, and so on and so forth. So, well, of course, but at that time, this was not known. So, and this appeared several times that the first result was obtained by a method of moments, and later you get new knowledge on these objects and on limits and so on. But sometimes the method of moment was the best what you could do. And there are some other problems. I don't want to go to this, but the method of moments is quite strong, mostly if you have no other methods available. There is, of course, a problem if you want to prove a central limit theorem with the method of moments. There is because you need the centered moments to get convergence for a central limit theorem, and there are oscillations. So if you expand the centered moments and you just know the moments of xn, then there are oscillations, and they are big because, for example, if the xn has expected value of size n, then the expected value of xn to the r will be of size n to the r at least. But here the variance is usually also of size n. So the left-hand side might be of size n to the r, and the right-hand side of size n to r over 2, which is much, much smaller. And so there must be some oscillation. So it's not a good a hint to use the method of moments for proving a central limit theorem. But there are people around, so Cinque and others, that can work with that. And for example, he also considers recursive random variables that satisfy a distributional recursive equation. And then what they did do was they got some recurrences for the centered moments, starting with the moment generating function of centered random variable and so on and so forth. This is a technically highly involved method, and I don't want to talk about that. But so anyway, it applies in many cases, and but it's not easy to handle. But the problem is always to get hands on the centered moments. This can be completely avoided, for example, by another theorem by Cinque, the celebrated quasi-power theorem that says if you have the probability generating function behaves like a power, so of this form, and there are some other things around, but it mainly behaves like the power of a function with some technical conditions that are quite natural, then you automatically get central limit theorem, and the proof is not very difficult because you just use this representation and Levy's theorem with the characteristic function, and you immediately get it in few lines. If you just want to prove that, if you want to get expected value invariance and even more, or tail estimates and so on and so forth, local limit theorems, you have to work a little more and you use more assumptions, but essentially you need this property. And this is really quite strong. And before I go back to the method of moments, revisit it, I want to recall some of these applications of this quasi-power theorem. And this applies in particular if you have a moving singularity. What do I mean with that? So that if you have this bivalent generating function in C and U, then the asymptotic leading term in this sense should behave like that you have a function that has a singularity, for example, at 1, and this part can be written in f of C divided by rho of U, where rho of U is some proper function in U. So this means that if you fix U, that rho of U is then the radius of convergence. And this, of course, if rho is varying, then this singularity moves if you vary U. And of course, if you fix U to 1, then you get the counting generating function and so on and so forth. And because, as we've seen before, the probability generating function is just the ratio of these two coefficients. And of course, if you have the singular behavior of f, then you can write the nth coefficient in this way. And the moving singularity appears here as a power of n, of course, minus n. And so you get that the probability generating function behaves like a power in n. So this means that the assumption here, you have to be careful with the error term a little, but you get a behavior of that kind. And this means that if you have a moving singularity, then you automatically get a central limit theorem. And this is the reason why this analytic combinatoric method is that powerful, and that's why the central limit theorem appears in so many cases. And a particular case where you have your moving singularity, if you have a function equation for your bivalent generating function. So of course, if you fix U, then this is just the equation. And when this equation gets singular, so then usually get a square root singularity, and then they have a moving square root singularity. So you get a central limit theorem just out of this equation, or if you have a system of equations. So this is very easy. And I just want to give you a quite old example for that. So again, concerning the problem, you have a big structure. Here is this big structure is a tree, and you have a special pattern, I call this. So this is a tree that looks like that. And you want to count how often this structure, substructure appears in the tree. And what you have to do is to find the bivalent generating function for that. And well, so you have to take care of occurrences of this structure, the substructure. And what you usually do is that you take trees recursively, starting from the root and so on. And of course, these occurrences of the substructures are additive, which is nice, but you have to take care what is going on around the root. And in this case, it turns out that you have to distinguish between 11 cases. The first case is where the root has certainly no additional occurrence, and so on and so forth. So you divide it into 11 distinct parts, and then you find recurrences on this path. For example, the third part can be written in this form that it looks like A0 and A2, or A0 and A3, and so on and so forth. And you also can count how often that you get here. In this case, is you always get one additional occurrence of your pattern. So you have an additional variable u here in this recurrence, and you get a system of equations. And if you have a system of equation, you have a moving singularity usually, you get a central limit theorem. So this was a paper in 2008. And its theorem says that if you fix any pattern in the tree and you count off with the peers, then you get automatically, say, a central limit theorem. The problem is just the combinatorics. There is a similar theorem if you consider subtrees, but subtrees are more difficult to handle than patterns, interestingly. And in another paper, together with Ramos and Ruhe, in 2017, we could prove that the theorem extends to subtrees and more generally to subgraphs, counts of subcritical graph classes like series parallel graphs. So it's not only true for trees, but also for other kinds of graph classes. Subcritical, I don't define that, but subcritical has a graph structure that looks like a tree if you look from a large distance. So it has a continuum random tree as a scaling limit. So this is, for example, true for series parallel graphs. And here you get the same result, that the number of occurrences of a given subgraph, the number of occurrences satisfies the central limit theorem. The point is that now you have to use an infinite system of equations instead of a finite system of equations, but still you can prove that there is a moving singularity and you get automatically a central limit theorem. But these examples already show that it gets more and more difficult to stay in this context of analytic combinatorics to get explicitly or implicitly a relation for your bivariate generating function and to observe a moving singularity. So this is the problem. What can you do if this doesn't work? And what I want to show today is that you can work with moments, but not with centered moments. So this is what I don't want to suggest, but it turned out that you can use other moments, namely the factorial moments. They don't differ that much to the usual moments, but they are not centered. Why factorial moments? So what are factorial moments? So factorial moments are just expected value is the factorial moments, but also the expected value of x times x minus 1 and so on. So this is the factorial moment, and they are very natural in the context of bivariate generating functions. So of course I don't want to use them, but going back to bivariate generating functions, if you just take the rth derivative of this bivariate generating function at u and in respect to u and then set u to 1, then again the ratio of these two coefficients is then just the r's factorial moments of your random variable of interest. So with the help of the bivariate generating function, you can get this moment very directly. So similar as before. So this is just an extension of the average case analysis. Say you get the first moment, the second moment, or x times x minus 1, and so on, and you can work with it. Or, and there is another remark, there is a very simple combinatorial interpretation of the factorial moments. So this is, so if we say suppose it's a counting parameter, so you count the number of occurrences of like pattern in a tree, for example, then what are you computing with the factorial moments? This is 1 over Cn, so this is normalization, times this sum here. And what does this sum mean? So what are you counting here are these objects, depending on the number of occurrences of this parameter. And then you multiply this with k times k minus 1 times k minus r plus 1. So you multiply it with r factors. So, and the combinatorial interpretation is very simple. What you're doing, you take an object and then you mark r different occurrences of your substructure. So if this appears k times here, then you have k choices to mark the first one. You have k minus 1 to mark the second one, and so on. So this is a combinatorial interpretation. So to compute, in order to compute these factorial moments, you can also do it combinatorially, and this will be used later. So let's do a very simple first exercise. Compute the factorial moments of the binomial distribution. So here we know that there is a central limit theorem. So there is no doubt on that. But the factorial moments are also very easy to compute. And you see, this is just n times n minus 1 and so on times n minus r plus 1 times p to the r. And if you write it in n times p to the r, n times p is the expected value, then you get the correcting factor of this form, e to minus r square over 2n. So if r is not too big, say up to square root n. And this is the first interesting observation. If you don't fix r to be 1, 2, or 3, but if you get r big, so up to square root of n, then this factor will count. And the question was, and this goes back to Gao and Wormold, is the converse statement also true? Suppose that you have a random variable where the factorial moments behave as they are here. So for example, n times p to the r times e to minus r square over 2n, say, and r is of this size. Does it also follow that you have a central limit theorem? And the answer is yes. And this is interesting because it's not necessary to center. But on the other hand, you have to get r quite big. So this is the theorem, or well, I called it lemma, but it's a theorem by Gao and Wormold. It was mentioned today from 2004 that the converse is true. So you have a random variable with mean mu n and variance sigma n square, satisfy some growth conditions, and you have the property that the factorial moments behave asymptotically as stated here, uniformly in a range for r between the two constants times mu n divided by sigma n. And in our case, this means that the r is of size square root n. It need not go up to 0. It's sufficient that it's between two constant times square root n. And then you get a central limit theorem just from that. So this, but how can you check these kind of conditions? It seems to be difficult to get some hands on all these factorial moments. Well, for the binomial distributions was easy, and it turns. Yes.
I can ask a naive question.
Yes.
There's no assumption that the distribution is characterized by the moments here, as we had at the very beginning.
Yeah, but the central limit theorem, the normal distribution is characterized by the moments.
Okay, that's
okay. Okay. So, but there is a simple observation actually that if you have a quasi-power situation, as for the binomial distribution, then you get this property that the factorial moments behave as they should. Namely, they have exactly this form as it was proposed here by Gar and Wormald. So this is not, of course, this is consistent with the quasi-power theorem. So now we have a second proof of the quasi-power theorem, a quite involved one, because you just start with this, then you prove this property, and then you apply the theorem by Gar and Wormald. Well, this I would not suggest to do so, but it works. And just to show you this here, this small lemma here, this is the only proof that I show you. So there are some full proofs. This is the only full proof that I show to you. So you see that the factorial moments can be represented. There's just coefficients of the probability generating functions if you expand it at u equals 1. So you can rewrite it as an integral around u equals 1, so a complex integral, and you just choose the radius in a proper way of this cycle around 1, and then you use the asymptotic behavior of your probability generating function and compute it, and you directly get what. So it's really not very difficult. So it's just, so finally you have to evaluate the Laplace integral as usual. And everything fits together, and so you get all these factors, and then this, and you of course you need Stirling's formula. But this integral really only the first part of the integral is of importance. The other parts go to the end. Okay, and this method of moments or method of factorial moments was not used that much so far, as I know. So it was first used by Gar and Wormald in 2004, where they applied it to submap counts in random planar triangulations. I come back to planar maps later. In 2017, Luc and Kai used it for subtrees in conditional Golden-Watt trees. And today it was also already mentioned that there are multivariate versions of this theorem by Gar and Wormald. They have been proved independently by Ichenko and Wormald, and also by Gabriel, Cecilia, and Svante. It was presented today in the morning, and they applied them for different problems. So this method is used, and now I want to present you another application of this method of moments or method of factorial moments, namely for pattern counts in random planar maps. And this is a joint work with Eva Maria Heinzl and Nick Wormald. Actually, will be a combination of some analytic combinatorics. So everything that was mentioned before, or many things that was mentioned before, will be used also here in this proof. So what are planar maps? So planar maps are planar graphs embedded into the plane. So they might have double or multiple edges, loops, and so on. But usually they are rooted by a directed edge. This makes things easier, say the counting problem, because destroy symmetries and so on and so forth. And it's a good thing to have it rooted, because, well, you want to count this object, and there is a natural way of counting this object by deleting the root and looking what is left. And then there are several situations, and then you get a kind of recurrence and so on and so forth. And this goes back to Tat in the 60s of the 20th century, that there is a very nice formula for the number of different planar maps with n edges and rooted in this form. And this is, well, the asymptotics is 12 to the n times n to minus 5 over 2. And this minus 5 over 2 comes from the singularity that is not a square root singularity, but the singularity with exponents 3 over half. You see, the generating function is explicit. And it's not so easy to get this generating function, but the method that has been used, and it's quite a nice method, is this method by removing the root edge, and you get a recurrence. But there you don't get the direct recurrence. You have to add a so-called catalytic variable that is not necessary finally, but for the recurrence you need it. So you take the outer phase. So you have this. So you have the outer phase here, the infinite phase of this map. This has some valency. It's here. It's 1, 2, 3, 4, 5, 6, 7, 8 into account. And so you get a recurrence in this context. You put it into an equation, and here you see this catalytic variable is sometimes 1, sometimes not, and you get a so-called catalytic equation, or a discrete differential equation. It's also called discrete differential equation. But by binding C and V in a proper way, you can solve this equation. We get explicitly this function. These random planar maps are very well studied. They're very nice results. So this is a nice picture how they look like. And this surface that appears here is the called Brownian map. So it's in some sense similar to the continuum random tree, just for maps, and it is a universal limiting object. It's not only the limiting object for all random planar maps, it's also the limiting object for random quadrangulations, and there are many other kinds of maps that you could consider. There is also a so-called local limit. So if you look to the neighborhood of the root, say, then this stabilize in distribution. So there is a discrete limit of this neighborhood if you fix the radius of this neighborhood. And this is so a so-called local limit, and there are many proofs for this property. And you can also extend it to the neighborhood of a random vertex to get a Benjamin-Schramm limit. So I did this together with Benedikt Stuffler. So you have, but this is just a corollary from the previous theorem. But an interesting thing that you can get out of that is that if you have some counts, that you want to count the number of occurrences of a given local structure, say a pattern, then it turns out that the expected value of this counting variable, so you have a planar pattern and you count the number of occurrences of this pattern. I come back to the notion of a pattern in a moment. Then it directly follows from this Benjamin-Schramm limit that the first moment is linear, which is quite natural, that you have a linear number of occurrences if the size is linear. And this just comes from the fact that locally, if you take a random vertex, the behavior is the same in the limit locally. And of course, the question is there always a central limit theorem? So it's quite natural to get a central limit theorem. But in this case, it's different to prove. So, but what is a pattern? And this is the topic of the talk, maybe. What is the distribution of pattern counts in planar maps? So a pattern is, again, a kind of, well, a small planar map. And so this is a very easy example. So you have just two quadrangles, and they are put together, so with paths of length 2. This is the pattern. And there is, of course, a very simple pattern. So the easiest thing that you consider is just a phase. So you can also count just how often there is a phase of valency 4 or 3, counting a triangle phase, whatever. So this is the simplest pattern, is the phase of valency given valency R. Yeah, and so what we have in general is that the expected value, so the average case analysis is done, it's linear. And this is a simple consequence of this local limit. But we want to have more. We want to have a central limit theorem. But it turned out that this is not an easy problem at all. Well, there are some partial results. So of course, the result by Gar and Wormald is a special result. So they counted submaps in 3 connected maps count of 3 connected map in 2 connected triangulations. So this is very special, and the one point is that there are no intersections. So these 3 connected pattern cannot intersect, so they are all separated. This makes the counting more easy. Concerning maps, so some phase counts of random planar maps. There are 2 papers where I've been involved, one in 2019, one in 2013. And these were only phase counts. So this was only considering the simplest pattern at all, so just counting the phases. And the first result where going beyond phase counts was a result together with Guan Ru. He is somewhere here. Where is he? Yeah. So previous PhD students was part of his PhD thesis where he counted double triangles, which is just an edge and both faces attached to this edge are triangles. So this is the simplest thing. So it's even simpler than that. And even this case was more or less not this whole PhD thesis, but say 1/2 of the PhD thesis. So it was quite involved, and so it turned out that, or it seems that the methods that we're using there are limited because we used more or less classical methods, counting methods. But now we got a result for at least for a pattern with a so-called simple boundary, so that it's not too complicated pattern. So, like, for example, it applies to this pattern. So there is now a central limit theorem. But going back here to these results that we got, so we have been using different methods. So you know that there are many bijections between maps and trees or decorated trees, and so there is an idea to use these bijections. And there is the quadratic method that has been used by Tat and others to count planar maps by putting away the root edge, and then you get the catalytic equation and so on. And this can be also used, but one always uses the quasi-power theorem. But what the new method with the factorial moments uses pre-processing with the quasi-power theorem, and then using a combinatorial idea to get back to the moments. So let me start with the bijective method. I don't want to go very much into the details, but here it was quite general because we could choose the potential phase valencies. So if omega is, for example, 3, you only have triangulations. If it's just 4, you have quadrangulations. It's only the even numbers. You get bipartite maps and so on. So you can fix an arbitrary set of positive integers, might be really arbitrary, finite or infinite. And then you can consider the number of phases, just the phases of valency R, and you always get a central limit theorem. And you also get this universal exponent n-5/2 in all these cases, which is also quite interesting. So, and the bijection works with so-called mobiles, or there are different objects, but the bijection that we have been using are mobiles. Mobiles are kind of trees, and it doesn't look like a tree. Usually you would paint or draw a tree differently, but you will see in a moment why this mobile is drawn in that way. But it's just a tree with 2 different kinds of vertices, and the black vertices might have these small arrows there, and you count the degree of this vertex as the usual edges plus this arrow, so the degree of these vertex is 3. And there is a bijection between maps and mobiles. And this is the bijection. I don't go into the detail, but here is the map, and this is the mobile. And the point is that here you have a black vertex of degree 3, and this relates to a phase of valency 3, and so on and so forth. But and the point is that this kind of object, this is a rooted tree because here you have a root that relates to this root. And so these objects can be counted. You just have to define proper substructures of mobiles, and then you get some recursive relation. So you get a system of three equations, you get a moving singularity, and the maps are related to these solutions of this system. So you get a moving singularity, and the outcome is a central limit theorem. Sorry, where was it? Here, this is the theorem that you had a central limit theorem in this case, just exploiting this bijection. The problem is that, for example, if you have adjacent faces, then the corresponding vertices are not adjacent here in the tree. So to go beyond faces seems to be difficult, if not maybe not possible. So this was the first method, but this was limited, and it was limited to face counts. The second method that have been used here, that was the first paper, where we, together with Costa Panequito, we could apply it not only for planar maps, but also for two connected maps. Because, for example, if you take bijections, as far as I know, there are no bijections to trees or tree structures between two connected maps and some kind of tree. So you cannot consider two connected maps with these bijections. So, but in this case you can do, but three connected maps we cannot. This would be a real problem to do three connected maps. And here we also got a central limit theorem for this counting variables, so counting faces of valency R. And this is again the catalytic equation for the counting problem. And the point is, if you have and this has to be proved, that if you have this kind of catalytic equation where you have an additional variable u, that this should be also u, sorry, where you count maybe some other parameters, and you know that the function, if you put this parameter u to 1, has this kind of singularity, then you get a moving singularity in this context. So this was a necessary technical lemma, so that you get a moving singularity, and then you have to do the combinatorics, and this also works that you put away the root edge, and then you can you get a recurrence for the number of occurrences of faces of given size from this root extraction method, and you get an equation for this triple generating function. There is a catalytic variable, and there is another parameter that counts the number of faces of given size. Okay, and so you can apply therefore this lemma, and from this lemma you get a moving singularity and the central limit theorem. But these two methods only work for face counts. And then I already mentioned this is by Guan-Ru, where he considered double triangles. So a very simple pattern. And it turned, well, of course, there is a central limit theorem, but the problem was that the combinatorics is quite involved. So in order to get hands on the number of double triangles, it turned out that you have to use a system of catalytic equations. So the recurrence is very involved. The combinatorics, so this is a picture done by Guan-Ru, is quite involved. So to get some recurrence, you start with a map, you put away the root, and then there's different cases, and you have to go into several levels, and finally using also some tricks with rerouting and so on and so forth, putting some edge somewhere, you get a recurrence relations, and this can be rewritten into a final system of catalytic equations. The drawback of this method is that it is quite limited, so we could not do any more involved pattern with this method. Anyway, we got the central limit theorem. Okay. So now what can we do with general pattern? And this is the topic of the talk, say. So we do it with vectorial moments, with the method of moments by Gao and Wormwood. So, and here I come back to this combinatorial interpretation. So if we have a pattern, so this should be also P, sorry. No, it's correct. So this, so the factorial moments is just a ratio of two numbers. So the denominator is just the number of maps of size n, and the numerator is the number of maps of size n with R distinguished and ordered occurrences of this pattern. So we have to get some knowledge of these numbers. And the idea is quite simple, but it's but to do it actually then, is in particular with high moments, is not that easy. So if I want to, well, the question is, I want to count maps where I distinguish an occurrence of this pattern. So if I take this pattern, so I mark it. So this is my pattern that I take here. Then, of course, I can remove these two edges. So what I get is again a map with two edges less. And what I have marked is now a phase of valency 4. This is an easy process. And the point is that I can go back. I can go back actually in two ways. So I have to put two edges inside, so the size is enlarged by 2, and there are two ways of doing it. And this point is I can go back and forth. So this means if I want to compute the expected value of the number of occurrences of this pattern, just the average case analysis, then what I have to do is I take the the double generating function of where U counts the number of foregons, so the number of occurrences of a foregone as a phase of valency 4. Poor means that there are no double edges and so on for that, so this is a technical issue. Then I have to put there two edges, and I have to put a factor of 2 because I have two ways of putting them. So it's a very easy stuff. So of course I can put out the factor 2. I can put away this factor c squared by shifting, and then this is just technical. So then I get here, I put this here, so this is easy to get. And here, what I get here, this is just the first moment for the number of phases of valency 4 times the correcting factor. And therefore, I get mu4, which is the expected value, times 2 times, n minus 2. This comes from this part here. And 1/12 square is this correcting factor because the rate of convergence is 1/12. So you can get out the expected value of the number of patterns if you know the expected value of the number of foregons. And you can also do it for the second factorial moments the same way. So if I have two occurrences of this pattern, if they are apart, everything is fine, but they can come together. So there is some overlaps, and this makes the problem combinatorially. So you have different situations where they can overlap. So this is a simple case. Here what you're doing, you are pointing at these two occurrences of this pattern, then you put away the internal edges. So you have again this map with these two occurrences of two phases of valency 4. So you can relate it to the expected value or the second factorial moment of the number of phases of valency 4. And here, well, this is a little bit more complicated because here you have one phase of valency 4, and now you have to put there 4 edges, And there are, again, two ways of putting them and so on. And it gets more and more complicated. But you can relate the second factorial moment by the second factorial moment of this and the first factorial moment of this and that. But here you have faces of length 4, and here you have faces of length 2. Well, so you can relate all this. So, but we know already that if you just count the number of faces of length 4, we have this quasi-power situation. So with the help of the lemma from before, we get that the factorial moments of the faces of length 4 behave as they should behave. And with the help of this method, by this combinatorial method, you can get also the factorial moments, for the number of occurrences of this pattern. Even for the second factorial moments, there are some problems, as you see, because there's a combinatorial problem, and this gets worse because of several reasons. One reason is that there might be overlaps of several occurrences of this pattern, and this is a combinatorial problem. But the good message is they are negligible, so you only have to consider double occurrences. Okay, so this helps, but finally you have to do the following maybe. So this is the picture, the general picture. What you really want to have is on the left upper part. So you have this, you distinguish in this case 10 occurrences of this pattern. So only with double occurrences, of course. And then you have to remove the labels. Then you have to remove the edges inside, and then you have to label them again, to count them as factorial moments, now as phase counts, and then you go back and so forth. And this is a quite involved structure, but and this I didn't want to show it to you. This is a very big calculation, but finally you get exactly what you want to have, and you get a central limit theorem for this for these pattern counts in random planar map. So this is the result. So we get it for a pattern with a simple boundary, but this is maybe just the first step. So and maybe this is not the final answer. So maybe there are better methods to work on that. But at least this is a first result into this in this context. And of course, there are many open problems. So what I would really like to do would be, so say, phase counts in planar graphs. So we know that the planar graphs have a Benjamini-Schramm limit. So we get first moments by this method. So we get that phase counts are linear. So this has been known before. But there is no result only for, well, I think, vertex, you have vertex counts because there are no faces, so you don't embed it. So phase valency, so degree, so vertex counts of given degree. So only vertices of degree 2 can be analyzed, but this is a very simple stuff. But there are no results. And the first result would be to get something for 3 connected planar maps, because 3 planar maps are 3 connected planar graphs because of the unique embedding by Whitney and so on. So a general problem might be the following: that you have a structure with a Benjamini-Schramm limit. So in all the examples that I mentioned, there was a Benjamini-Schramm limit, and you have a local structure, and you want to count how often this local structure appears in your object. And if you have a Benjamini-Schramm limit, then you get the first moment for that. It is linear in the size. But is there a general theorem? What conditions do you need for this limiting object to get a central limit theorem for that? This is maybe the overall goal, and maybe also the idea of all the problems that I presented to you. So thank you very much.
So, are there any questions? Okay, yes, yeah. No, Cecile explained that for benefit of those watching on Zoom, it's good to have.
Do we need to press?
It's a micro.
yes, I
This
think
is
you
just a
press-
micro.
I'll try this. So just on that last slide, marvelous talk. Thank you very much. On the last slide, are there particular Benjamin limits for which it is?
Hmm?
So are there some classes of Benjamin-Schramm limits where such a result is?
Not that I know. So I don't know. So this is just the overall problem that I formulated. So and that I would like to see an answer or some ideas how to prove that. So there are some ideas, but there is no final, of course, far away from a final answer. We just have examples or instances where this is where we get the central limit theorem. For example, here, and we expect it in many other cases. But it would be also nice to see an example where there is no central limit theorem.
Okay, yes, take next. Yeah, there's the one. Yeah.
Yeah, yes, speak loudly. It works.
Yeah, okay. Somewhere at the beginning, you mentioned that patterns versus subgraphs, the counting is much different.
Yeah.
Do you have kind of an explanation or an intricate explanation why this is the case? Why the analysis is different?
It is just turns out to be more complicated because if your patterns or if it's an induced subgraph, say, then it's it's more rigid. So there are too many cases.
Okay, any more questions? Yeah. Ah, there, one.
Through this one method,
Yes,
what will work out
to work out
convergence rates?
to work out conversions rate. So the question was if you can get out the convergence rate, various and bounds and so on. I would say yes. The point is, yeah. So the method is that it goes to it proves that the convergence to the moment generating function. Svante knows better. And this course has generalized it in multivariate case. And so everything is explicit more or less. And by exploiting, I think you certainly get some Taylor estimates because you have the moment generating function. If you get more than that, I don't know it, but this could be exploited, yes. But
Oh, I cannot add anything. I have not so cognition. I agree that it seems very likely one can get something for precisely the reason you say, and whether one can get short results or not, I cannot say, but maybe.
yeah, at least something should be boosted. So you get the moment generating function, and so you get something, but maybe not very precisely. Maybe some additional properties are needed.
Okay, anyone else? Okay, so then let's thank Michael again for a very interesting talk here.